Paul is a postdoctoral fellow at York University in Toronto, and he's going to talk about collision-induced absorption of all these chemicals and their effects on ancient Martian atmospheres. So over to you, Paul.
Thank you, Gordon. So as Gordon said, I'm going to be talking about ancient Mars. So as a planetary scientist, and I'm going to just go to the next slide, please. All right, so this is really, planetary sciences are a large interdisciplinary effort. So particularly we're tackling this problem of ancient Mars. And the problem I'm referring to is this sort of paradox between what we see on the surface and we see in the atmosphere. So if you look at the surface of Mars, the images on the side there are comparing surface features on Mars to surface features on Earth. And there's a lot of stuff that looks similar to flowing water structures on Earth. Valley networks, lakes, shorelines, effects of glaciation. So that would imply that, at one point in time, Mars had flowing water. If you look at the composition of the surface from a chemistry perspective, a lot of the substances you see there can only sort of form in certain temperature ranges. So phyllosilicates and lack of carbonates, those would imply that Mars is also warm at one point in time. But now this sort of warm and wet early Mars is at odds with what we know about the Martian atmosphere. So several million years ago, the sun was actually a little weaker than it is today. So you would have less energy coming to warm the surface of the planet. You can look at the atmospheric pressure on Mars today and try and model it backwards to what it was back in the past, and you would have a very low atmospheric pressure, which again would result in a cold Mars, ancient Mars. And then again, sort of coming back to this sort of chemistry idea, depending on what chemical compounds you see at the surface would imply what chemical compounds could have been in the atmosphere, and there's not really strong greenhouse gases. So this is the big paradox in the planetary science community of how can Mars have been warm and wet from a geological perspective, and yet also looks like it would be cold from an atmospheric perspective. And this is really what this talk is about in trying to work towards understanding this. Next slide, please. So one potential way to get around this issue is collision-induced absorption. What this is when you have two molecules in a gas, each molecule can absorb atmospheric radiation in its own way. And those are the single line absorptions. But if two molecules collide together, there's a temporary moment in time where the two molecules form a supramolecular complex. And that two molecule complex has its own absorption features. So if you're to look at Beer-Lambert's law for a gas mixture, which is this equation I have there, you have, let's say in this gas mixture, you have carbon dioxide plus one other species, in this case, either methane or hydrogen gas. Your total absorption is going to be absorption due to individual CO2 molecules, your absorption due to individual hydrogen molecules, but also these combined absorption features of a CO2 molecule interacting with a CO2 molecule, hydrogen interacting with hydrogen, and then the mixed term of CO2 and hydrogen or CO2 and methane. And it was these CIA, collision-induced absorption features, CIA, that was lacking from a lot of Martian models. And so as paper came out that suggested that maybe this was the missing key. And that's sort of what's shown in this figure in the corner. This is from Wordsworth et al. 2015. And what they were showing is if you were to include CIA from CO2 with hydrogen, CO2 with methane, you have some weak but significant absorption in a little atmospheric window on the Mars spectrum. Now, one thing I should mention that those lines there were actually theoretical lines. The big problem here, one reason that no one ever included this in the first place was these lines, this measurement didn't exist. No one had measured CO2 plus methane or CO2 plus hydrogen. People had done nitrogen and hydrogen, nitrogen and methane, and so people tried to use those as a proxy, and those are those dotted lines in that figure, but they're quite a bit weaker than what the Wordsworth group simulated to these CIAs to be. The one thing I want to draw in that figure there is it is a log scale on the y-axis. So it is a small, CIAs are typically a very small effect, but because they're significant in this atmospheric window on Mars, they could prove to be quite powerful. In order to measure those CIA effects, you really, because it's a weak feature, you want a long path length. So if you're going to try and measure this in the lab, you look at Beer-Lambert's law again, the first term there is this L, which is the optical path length through your sample. So we figured we would take a crack at trying to measure these CIAs experimentally and confirm Wordsworth's theoretical calculation. Next slide, please. So to do this, we traveled to the Canadian Light Source Synchrotron that is located in Saskatoon. The reason we went there is they have experimental facilities that we did not have at York University, but would be useful for this experiment. Next slide. So in particular is the Far-IR Beamline, and they have what's called a white cell. So that's that bottom schematic there. A white cell is a spectroscopy gas cell, but you put mirrors at both ends of the chamber. So when your light beam comes in, you can bounce it back and forth repeatedly between the cells. So even though your base cell length is only 2 meters long, depending on the number of bounces you can get longer distances. In particular, this one at the CLS is able to go up to about 70 meters. And a technique we're going to use here to measure these absorption cross sections is Fourier transform spectroscopy. So we had to do the light source. I will say it's a very busy place. It's hard to get beam time there. So we were awarded about a month's worth of beam time where we would be able to run 24-hour shifts. The facility is open 24 hours. So my team and I, we were there, we were doing shifts, and we were trying to get all these temperature-dependent cross-section measurements to compare to the theory. So let's go to next slide. So this is the CO2-CH4 CIA that we were able to measure. So we were taking it at 3 different temperatures. The black line with the gray shading is our experimental results. The dotted red line is the Wordsworth simulation that we were trying to validate. The green line is that nitrogen value. As I said, nitrogen was the original proxy used in this story, and so we were including that to show how much stronger this effect actually is compared to nitrogen. There's a blue line, which is while we were trying to do these measurements, there was a group in France who was doing the same thing, who had the same idea we did. They only did a room temperature measurement, not temperature dependence, and their result is shown there. They also were able to do theoretical calculations at different temperatures, which is their blue solid line in the other temperature plots. Part of the reason why the Francis group error bars are much better than ours is the short answer is their white cell has a longer path length, which will help with singleton noise. They also were allowed to do higher gas mixing ratios than we were. Methane and hydrogen are explosive, so the CLS was not happy about us trying to put a lot of that gas in a tight and closed space. They didn't like the idea of us making bombs in their basement. So we were limited on how much of those gases we could put in the cell, which also drives our signal down, which unfortunately increases our error. However, we can still, despite the noisiness of our signal, we see agreement with the Francis group's room temperature measurement, and we see that our measurement agrees quite well with what they predict for other temperatures. But the start of this was to compare to Wordsworth's value, and we see that Wordsworth basically overestimated by almost a factor of 2. Moving, next slide, please. So now this is for hydrogen. Same story. This is a little messier, mainly because hydrogen is more explosive than methane, and we were further limited on how much we can put in methane in the chamber, so we had to do even less mixing ratios. We also noticed that there was more water contamination in our hydrogen experiment. So water absorbs quite strongly in these wavelength ranges, and that was a big source of uncertainty in my data. So while this isn't the nicest data set, again, we kind of see that this is about half as strong as Wordsworth predicted and agrees quite well with what the people in France have come up as well. Okay, next slide, please. So now that we have an updated CIA spectrum, the logical thing to do would be to go back and reevaluate these Martian climate models to see if, is this the saving grace for water on Mars? Could this solve this whole paradox? So we partnered with a fellow out of Japan named Ramsey Ramirez, who had done some of these early Mars climate models. And we said, hey, do you want to work on this with us? We have these new updated cross sections. And he said yes. So he just basically plugged into his existing code our updated CIA values. So his code is a single column cloud-free radiative climate model. And what he did, he simulates a few things for us. This first one here is surface temperature as a function of pressure. So your total atmospheric pressure. And then he's looking at different mixing ratios of gases within there. So the key thing to see is, if you look at the graph, so dotted lines are with the updated, so dotted lines are Wordsworth's original prediction, and solid lines are using our new CIA values, which are half as strong. So first of all, you see obviously that with the weaker CIA values, you need to have more gas or higher pressures in order to get increased warming. We're limited on these graphs by going about 2 bar. That's because a lot of Mars models suggest that at most the ancient Mars atmosphere was no more than 2 bar. So this supposed to be a problem for methane, the lower panel there, where limited at 2 bar and even up to 10% methane, you never really crack this freezing point of water. You also don't want to go more than 10% of methane, because if you go above that, you start forming a chemical haze that will actually provide a cooling effect on Mars. However, for hydrogen, the upper panel, you can see that with a 2 bar atmosphere and even as low as 5% hydrogen, you can get liquid water on Mars. Next slide, please. So another thing we modeled is the planetary albedo. So with increasing concentrations of methane or hydrogen, you're going to have increased scattering, which will lower the albedo, which is seen by the colored lines getting weaker. Comparing the Wordsworth absorption cross-section values to our updated ones, for hydrogen, there is an effect on the planetary albedo. There really isn't one with methane. The reason for this being, because we saw on the previous slide, methane doesn't really achieve significant warming, but because hydrogen does make things warmer, that will in turn increase the amount of water vapor, which will have an impact on the planetary albedo. Next slide. So as a last thing, we looked at temperature profiles as a function of altitude. Again, comparing if we use the old CIA values with our newer ones. And what we see here is in the upper atmosphere, it doesn't change much which CIA values you use, but as you get down to the surface, things start to diverge and it becomes a significant effect using the correct CIA strength. And then last slide. So in conclusion, these were the first temperature-dependent experimental measurements of these CIA values. They agreed quite well with previous experimental groups' publication. They ultimately disproved Wordsworth's original model, which was twice as strong as it should have been, but that's okay when we're running these radio transfer calculations now with the updated one, is we find that hydrogen works still as a potential greenhouse gas. Methane, however, is not quite as promising. Although this isn't necessarily the end of the story, because hydrogen, unfortunately, is a very light molecule and happens to escape atmospheres quite readily, so it may not stick around long enough. Now, to address that issue, people have looked at this idea of transient warming, where you would have maybe a volcanic eruption or comets come and dump a lot of hydrogen or methane on the surface, and it sticks around for a couple 100,000 years, and you get periods of warming, then you go cold again, and then you have another volcanic eruption, another comet, and then you can get warmed again. So this is the current theory about why Mars would be potentially could have been warm and wet, but also still cold as it is today. Thank you. Any questions?
Interesting presentation. Quite very different as we've gone from social media to the Martian atmosphere. Well, you mentioned at one point the idea that the sun was so much lighter, yet I wasn't, or at least less energetic, giving off things. I wasn't sure how that related to the fact that the Mars seemed to be warmer.
No, so that's what that just adds to the challenge of a warm or ancient Mars. So several million years ago, the sun is not outputting as much energy, so all planets would be colder than today. So it makes the challenge even more difficult to get a warm enough surface.
And a question came from somebody else, Fred Conway, saying, how is this relevant to the process of terrestrial conditions now in that sense? How do you relate that? I'm assuming that's what the question is.
This is relevant in terms of, I would say, CIA calculations and modeling. So, I mean, collision-induced absorptions will exist in any gas mixture. And if you want the most accurate radiative transfer models possible, you probably should consider including those in. And part of what this, it's not just that we did an experimental confirmation of one set, we also show how that calculation that was originally done was off by a factor of 2. So for people who want to potentially go and model other CIA spectra, it's something to take note that you might want to be careful in how you do those calculations. So, because these this deriving experimental CIA is quite difficult, but if you can do reliable modeling calculations of them, that would be beneficial.
Good. Well, thank you very much, Paul, and thanks to all of the speakers who've been here. We've had attendance over this event from, well, we were over 100 at times. We've gone up